Welcome to this comprehensive one-shot explainer. Today, we are diving deep into a complete top-to-bottom breakdown of periodic classification and properties of elements. We're going to scale this across 3 difficulty tiers, starting right at your foundational board concepts, accelerating straight through NEET and JEE Main, and finally unpacking those notoriously tricky JEE Advanced edge cases. Let's see how it all comes together.
But hey, before we unlock the secrets of the atomic world, you're absolutely going to want to grab your essential inventory. Make sure to subscribe to the Masterclass 11 and 12 YouTube channel for full chapter revisions. And definitely join our Telegram channel. The link is right down there in the description, so you can download your free complete handwritten notes, formula cheat sheets, and previous year question worksheets. You'll need those.
Okay, here's our roadmap for today's explainer. We're covering position determination and periodic law, Zeph and radii trends, enthalpy exceptions, and finally, chemical trends. Let's jump right into Section 1, Modern Periodic Law and Position Determination. For decades, brilliant chemists were, kind of stuck. You had Dobereiner with his triads, Newlands with his octaves, and even the legendary Dmitri Mendeleev in 1869, and they all obsessed over arranging elements by atomic weight. It literally wasn't until 1913 that Henry Moseley came along and totally shifted the paradigm. He proved that the ultimate fundamental property of an element actually isn't its mass at all, but its atomic number. What's really fascinating here is how Moseley proved this mathematically. He bombarded elements with high-speed electrons and studied the resulting X-ray spectra. When he plotted the square root of the X-ray frequency against the atomic number, Z, he got a perfect straight line. I mean a mathematically perfect line. This completely rewrote the rules, giving birth to the modern periodic law as we know it today. So, with the atomic number as our guide, we can use this algorithmic step-by-step cheat code to find literally any element's position. First, find the preceding noble gas anchor. We'll call that Z-ref. The period of your mystery element is just the period of that noble gas plus 1. Next, writing out the condensed configuration reveals the block, which is determined by whichever subshell receives the absolute last entering electron. Finally, just apply the group rule for that specific block, and boom, you have its instant location. Now, for the really heavy hitters, elements with an atomic number over 100, we standardly use systematic IUPAC numerical roots instead of common names right off the bat. These roots correspond directly to the digits in the atomic number. So, element 104 becomes unnil quadrium, or UNQ. It's a highly logical naming system, perfect for newly synthesized elements where we don't have a catchy name for them yet. But watch out, because you absolutely have to know these configuration anomalies, especially for JEE Advanced. Everyone knows chromium and copper borrow an s electron to half-fill or fully fill their d orbitals. But look at palladium. Palladium is uniquely interesting. It's literally the only element in the entire d block with absolutely 0 electrons in its outermost s orbital. Its configuration is 4d10 5s0. That is a perfect exam trap, just waiting to catch you off guard. Moving right along to Section 2, Zeph, radii trends, and oxides. First up, distinguishing exactly how atomic size is measured is key. Covalent radius measures overlapping orbitals, so naturally, it's the shortest distance. Metallic radius measures atoms touching in a crystal lattice. But the van der Waals radius, that one is always significantly larger because it measures the closest approach of 2 non-bonded atoms. There's 0 orbital overlap there, just a whole lot of empty space. And this chart brilliantly illustrates the macro trend. You can see the atomic radius steadily shrinking as we move across the second period, going from lithium at 1.23 angstroms all the way down to fluorine at 0.72 angstroms. Why does this happen? Well, protons are being added to the nucleus and electrons to the exact same shell, so that nucleus just pulls harder and harder, shrinking the whole atom. This inward nuclear pull is quantified using Slater's rules. Effective nuclear charge, or Zeph, equals the total atomic number minus the screening constant. Now, the crazy part is that the screening effect isn't uniform. The s orbitals shield really well, but d and f orbitals, they are terrible at it. This poor shielding leads to some fascinating size anomalies. It's the exact reason gallium is surprisingly smaller than aluminum right above it, and why zirconium and hafnium have virtually identical radii due to the lanthanide contraction. Oh, and for isoelectronic species, ions with the exact same number of electrons, the one with the most protons is always going to be the smallest. Beyond just size, you absolutely have to commit these specific oxide classifications to memory for advanced exams. Amphoteric oxides, The ones that swing both ways and react with both acids and bases include beryllium, aluminum, gallium, zinc, lead, and tin oxides. Meanwhile, your neutral oxides are nitrous oxide, nitric oxide, and carbon monoxide. Lock those in.
All right, Section 3, ionization and electron gain enthalpy exceptions. This is where the standard rules get thrown out the window.
Normally, we know ionization energy increases across a period. But look closely at this data. Beryllium is actually remarkably harder to ionize than boron, because beryllium sits on a perfectly stable, fully filled 2s orbital. Even wilder is that nitrogen's first ionization energy is higher than oxygen's. Nitrogen completely overpowers oxygen here due to the extreme symmetrical stability of its half-filled 2p orbital, which makes it incredibly stubborn when you try to remove that first electron.
-349. That number right there is the electron gain enthalpy of chlorine in kilojoules per mole. This is massive, especially when you consider that fluorine, despite being the most electronegative element on the entire periodic table, only has an electron gain enthalpy of -328. Why? Because chlorine releases way more energy when gaining an electron, since fluorine is just so tiny that trying to shove an electron into it creates massive interelectronic repulsion.
And these concepts build into some pretty extreme exceptions. For example, while nitrogen beats oxygen for that first electron, removing a second electron completely flips the script. Oxygen's second ionization energy is drastically higher because at that point, oxygen is the one sitting on that ultra-stable half-filled configuration. Also, take a look at group 13's first ionization energy. It isn't just a simple straight line down the group. It's this non-monotonic zigzag from boron to thallium, then gallium, aluminum, and indium, all driven by those alternating D and F block contractions we talked about earlier. And finally, Section 4, electronegativity, solubility, and chemical trends.
Let's start with electronegativity. You've got to know these Pauling scale benchmarks by heart. Fluorine is a 4.0, oxygen is 3.5, and nitrogen and chlorine tie at 3.0. These values are basically your master key for predicting bond polarity. And even cooler, these properties create fascinating diagonal relationships on the table. Like, why does lithium chemically mimic magnesium and beryllium mimic aluminum? It happens because their ionic potential, which is simply their charge divided by their radius squared, is almost exactly the same.
Then there's the inert pair effect. In the heavier p-Bock elements, think thallium, lead, and bismuth, the outermost s orbital electrons become incredibly reluctant to participate in bonding. This is a direct consequence of that poor shielding from the inner D and F electrons. The nucleus just pulls those s electrons in super tight. Because of this, lead is vastly more stable in a +2 oxidation state than a +4 state. Check out Statement 21 in this actual JEE Advanced paper. It tests this precise concept by asking you to verify the stability of lead compounds. The entire goal here is to connect the oxidizing power of lead +4 directly back to the inert pair effect, making the +2 state the more stable reality. Next up, solubility. For group 1 and 2 sulfates and carbonates, whether a salt dissolves is basically an epic battle of energies. It is hydration enthalpy, the energy released when water molecules surround the ions, fighting against lattice enthalpy, the energy rigidly locking the crystal together. If the hydration energy wins out and exceeds the lattice energy, the salt dissolves. If the lattice energy is stronger, like in barium sulfate, it's just going to sit there like a rock at the bottom of your test tube. Okay, I've got an active prediction challenge for you to wrap this up. Using the position-finding rules and the periodic trends we literally just mastered, how would you predict the exact chemical properties of elements that haven't even been discovered yet, like Z = 119 and Z = 120? Think about the preceding noble gas to guide your configuration.
Well, if we use oganescent element 118 as our anchor, the next electron has to drop straight into the 8s orbital. That means element 119 would be a group 1 alkali metal with an 8s1 configuration, forming an M2O oxide, and 120 would be an alkaline earth metal. It is just amazing how predictive this periodic table really is. Make sure to subscribe to the Masterclass 11 and 12 YouTube channel right now, and go grab those free PYQ worksheets in the Telegram link below to test this all out yourself. Knowing the raw predictive power of the periodic table, what other hidden trends are just waiting to be discovered out there in the heavy elements? Think about it, and I'll catch you in the next explainer.